Good afternoon, everyone, and welcome to another NU at Noon. So just my usual reminders, I just want to make sure that everyone keeps their phone muted throughout the presentation. Also want to make sure that when we do the Q&A portion at the end of the presentation, you can enter your questions into the chat box and I'll read those aloud for our presenters. And then just as a final reminder, we are recording this meeting so that you can view it in the future and for anyone who may not have been able to attend. So just so you're aware, this is being recorded. And so with that, I will turn it over to Joe Hunt to introduce our presenters.
Well, thank you, Ashley. You know, shortly after I entered Northeastern as a freshman, that fall, the Russians launched their first space satellite, Sputnik. And since then, there's been a continued interest in space exploration, much of it about visiting the moon, and especially in finding out in detail what's on the dark side of the moon that can never be seen from Earth. During the same period, technological and computer advances have led to vast improvements and interest in robotics. Today's presentation, Exploring Permanently Shadowed Region of the Moon, combines both these topics, moon exploration and robots. Our presenter will be Alireza Ramezani, who has a PhD in mechanical engineering and is currently an assistant professor of electrical and computer engineering. He's published numerous much cited research papers, and interestingly, one of his many robotic interests relates to robotic designs that have been inspired by biology. Now he, along with the director of the university's Institute of Experimental Robotics, Taskin Potter, are both monitoring the progress and objectives of a team of Northeastern students who, through the use of a grant from NASA, are developing two four-legged robots that can explore the permanently shadowed regions of the moon. So with that, a warm welcome to our presenter, and to begin the presentation, I turn it over to him.
Great, thank you very much. And hello to everyone. Thank you for your time. And I want to say a big thank you to our alumni and our NU Alumni Center for organizing these seminars. I'm also thankful to my colleague, Tashkin Padir. I think much of the success that we have had in the past year in securing these kind of grants from NASA has been established based on the invaluable work that Tashkin has done with previous students. This is not the first time Northeastern students get prestigious awards and show they can do good projects with NASA. In the past, we have been able to accomplish that under Tashkin's leadership. So today, I'm going to just give you a very brief overview of this NASA Big Idea project that lately we were shortlisted among many schools across the nation, and I'll start with a very brief overview of what is this program and what is the importance of projects like this for NASA, and how NASA is going to use this results to enhance its capabilities for outer space explorations. I present the solution that we proposed to NASA referees, and how these solutions are different from traditional solutions that NASA has used in the past. And I conclude my presentation with two more projects related to space explorations, and they fall on the other side of I would call a spectrum of mobility. mainly using aerial mobility for space explorations, and give you a very brief overview on those projects as well. But first, let me start off by NASA Big Idea and what are the goals that NASA is pursuing and what we did in the past year. So in 2020, a team was selected as one of the winners at NASA Big Idea Challenge, and Big Idea stands for Breakthrough, Innovative, and Game-Changing basically challenge. Our team was given $90K to build a two-module system, including a legged rover, which is called Scout. And down the road, I briefly describe this platform, what is that? And a support module called Doghouse, which is essentially a charging station, and to help NASA explore Moon's permanently shadowed regions. But what is Big Idea? What is the goal? What is the objective? The Big Idea Challenge, it's mainly an initiative supporting NASA's GCD program efforts, which stands for Game Changing Development Program. And the idea is to rapidly mature, innovative, and high impact capabilities that allow NASA to explore unknown environments. This competition is intended to be an open innovation challenge, meaning there are minimal constraints in such a way that teams and students can genuinely create and develop out-of-the-box solutions. Every year comes with a new topic, a new challenge. In 2020, Big Idea Challenge was seeking innovative solutions and concepts and technologies that mainly can allow NASA to effectively explore PSRs for some important reasons that I'm going to briefly talk about it. Before I dig into the proposed solution, let me just give you a very brief background of the works that NASA has done in the past to understand surface composition of the Moon. Lunar surface has been perhaps studied more than any other celestial object, and these studies go back to late 60s before Apollo landing, and 5 lunar orbiter missions were launched in about 1966 through 67, all with the purpose of mapping lunar surface remotely. All of these missions were successful. A large extent of the lunar surface was photographed with impressive resolution, given the technological barriers that existed at the time. The first 3 missions, you see the result from some of the photos from those missions, were detected to basically image 20 potential lunar landing sites, mainly selected based on some sort of Earth-based observations. The 4th and 5th missions were devoted to broader scientific objectives, and they were performed from high altitudes. And if you compare this images with the previous images, you can see the difference between the quality and the resolution. Lunar orbiter photographed the entire near side and 95% of the far side. And these missions revealed the hostility and complexity of this environment. Lunar Orbiter 5 completed the far side coverage and acquired impressively high resolution images up to 2-meter resolution of 36 pre-selected basically areas. These images revealed the unstructured and harsh lunar environment for the first time. And the hostility of this environment, as we will discuss this very briefly down the road, can easily surpass the levels within which astronauts can operate. Some of the examples that I can mention is like complete darkness, dust storms. These are like very, very challenging environments. Before I kind of motivate why NASA Big Idea is looking into using autonomous agents for lunar explorations, let me highlight a few recent findings, all achieved through remote sensing, and highlight some of the limitations. These days, NASA's objectives are towards mostly understanding lunar soil composition. For example, studying the presence of neutrons, which would be an indication of hydrogen, and by inference, an indication of water. As an example, I can mention a LAMP project, which stands for Lehman Alpha Mapping Project. And you see these figures from LAMP project. Through this project, NASA has seen lunar surface in the dark using UV light. This UV light is reflected off of the lunar surface. And the UV light used here, it's in a specific type of UV light called Lehman alpha, which is generated by stars and a thin gas of hydrogen atoms in space. So these two figures you see here show north and south poles were created in the first few years of LAMP observations. And interestingly, in this picture, bright areas reflecting lots of Lehman alpha UV light, while dark regions reflect little. Generally, there is an agreement between UV dark regions and the coldest shaded craters revealed by LRO, a few pictures that we saw in the previous slides. Likely explanation include the presence of UV absorbing materials that could easily vaporize, like water. Since sunlight and heat vaporize this material, it would tend to accumulate at the surface, like in darkest and coldest regions, which are PSRs. Another possibility is a chance that like surface properties here cause this phenomena. So identifying the root cause of this darkening requires closer imaging analysis, a closer inspection, and this has motivated NASA for in situ sensing of these environments. In fact, recent findings actually motivates this even further and motivates the deployment of autonomous agents to PSRs even more. In 2020, it's a fairly recent publication. Honeybell reported in Nature Astronomy widespread hydration was detected on lunar surface through observation of a characteristic absorption feature at 3 micrometer. So whether the hydration is molecular water, H2O, or other hydroxyl compounds is unknown. And there are no established methods to distinguish these two using remote methods. I mean, they have used some remote sensing approaches to get some partial results, but this kind of motivates the importance of sending autonomous agents to these these regions of the moon to better understand the soil composition and kind of to sample this environment. But what are the challenges? What are the limitations? What is that? First, keeping NASA away from pushing remote sensing boundaries. Second, what is keeping NASA away from sending agents and autonomous, for example, rovers to these PSRs? We know that moon exploration took place a long time ago. So in terms of what is limiting us in terms of remote sensing, I can identify two challenges. First, what's currently being used by NASA, which is passive sensing of UV light, is not controllable, is not adjustable, is not something that it is under control, because technically spacecrafts have to detect what has been reflected off of the surface. So this is very, very challenging. Second, at crater's rim, the intensity of these UV lights, it's not enough to permit drawing conclusions about whether ice absorbs UV light or this is led by surface irregularities, which is known that it can diffuse reflecting light. My team's strong motivation here is to deploy autonomous legged robots to PSRs to help exploring these environments, mainly by transmitting UV lights at PSRs, or help lunar orbiters such as LRO to detect water. In general, our goal at Silicon Synapse Lab is to understand how biological locomotion systems work and to navigate harsh environments. A broader scope of our research is that we want to apply the underlying mechanism of biological locomotion systems in autonomous mobile robots that could be deployed in unstructured and challenging environments. Biological systems pose extreme challenges at all levels. I can identify, for example, extremely nonlinear dynamics. Have multi-body, multi-degree of freedom architectures. We often see compliance or compliant components in animals. Capturing or copying these behaviors, it's extremely challenging, particularly looking at some of the animals that they can move several joints in a fraction of a second. Replicating these behaviors is kind of a very, very challenging robotic problem, but it is rewarding because the end result, the bio-inspired robot designs that come out of this design paradigms would be very more capable than traditional and existing and conventional methods that have been used so far. So let me see if I can play this. So these systems can be very, very powerful and can bring a fresh perspective in how mobility systems can be designed for outer space explorations as well. And this is our major goal and objective. The Scout and big idea was mainly motivated by a design that was finalized in 2019 before pandemic happened. And we ran through prototyping stage partly through pandemic, and experimentation is ongoing now. Let me give you a very brief summary of this story behind this platform. We call it a Scout, we call it Husky Caravan. What was the story of behind this platform that led us to propose this for lunar explorations? So this project started with the goal of creating morpho-functional robots that can morph from unmanned aerial systems to quadrupedal configuration and vice versa. And that was basically the initial idea. The idea was to mainly use these platforms for automated package delivery in residential environments. And aerial systems are 3 times faster than ground transportation. They can do a decent job at high altitudes. But when it comes to delivery of items and customers' doorsteps, they have difficulties. And that's why we came up to this morphofunctional design that could put together area and packet mobility to solve this challenge. And later, we also consider this for other applications such as lunar explorations. But what are the challenges of existing solutions? Why is that some of the field-based traditional ground robots that NASA has been using them for a while for moon explorations, Mars explorations, etc., simply fail to survive or fail to give effective solutions for PSR explorations? So I can identify 3 major challenges. I call them mobility-related challenges in regard to exploring moon's surface. First, pervasive and inescapable presence of dust. So the reports from astronauts who participated in previous lunar missions simply saying that the fine-grained dust clung to their helmets, devices, communication tools, and that was causing a lot of problems. And down the road, I'm going to show you a video of this. The second problem is solar energy and the challenges associated with harvesting solar energy. It sounds kind of counterintuitive. We used to think that solar energy is abundant on lunar surface, but the fact that there are various factors that doesn't allow us to effectively do energy harvesting on lunar surface, other than dust storms between lit and shadowed regions on the moon, which can cause significant difficulties in using solar panels, even in lit regions. Near total darkness, like in PSRs, due to the oblique angle of the sun, demands really extremely efficient robots that once they enter inside the PSRs, they are relied on their energetic efficiency of mobility, and they can survive for hours and hours and doing explorations. And the third challenge that I can identify is the complex regolith composition, which are fluffier at PSRs, and that may contain ice particles, can make mobility extremely challenging and slow. So let's take a look at some of these conventional solutions that NASA has used in the past, and some of you might know some of these examples, and why is that the solutions are not good solutions to explore moon surface. So let's start with the most famous one. Traditionally, when you look at almost all of NASA's rovers, they are wheeled ground robots. For instance, this LRV was a battery-powered 4-wheeled rover used in the moon in the last 3 missions of Apollo program. And it was a massive machine, like weighing about almost 500 pounds, and could carry about 1,000 pounds with 2 astronauts, equipments and lunar samples, you name it. It could reach a top speed of about 8 miles, a very, very impressive accomplishment, but it had difficulties like traversing lunar surface, which is extremely bumpy. Other famous examples, which are not, of course, used for lunar explorations, and they are mainly designed for Mars explorations are Curiosity and the Spirit. And in these designs, NASA looked at integrating kind of articulated architectures with wheeled mobility in order to be able to negotiate random rough terrain of these harsh environments. There's a fundamental problem with wheeled mobility, and if we want to simply speak of this fundamental problem, for a wheel to get over vertical obstacles, it has to be at least twice as tall as the vertical obstacle. So wheeled robots cannot navigate over obstacles. This is the main drawback of the systems, and can be even more challenging depending on the terrain, such as rocky terrain, sharp declines, or areas with low friction, which are really abundant on lunar surface. This is probably the most, I would say, articulated example that I can find in the archive of NASA Rovers, Athlete, which is a concept based on this articulated, legs with this, 1 degree of freedom wheels attached to the leg ends. Athlete could use these wheels for driving over like stable, gently rolling terrain, but each limb could also be used as a general purpose leg. In the latter case, wheels could be locked and used as feet to walk out of like excessively soft, obstacle-laden, steep, or otherwise extreme terrain. However, this was not an invention to be used for exploration purpose, and it was mainly a heavy lift utility vehicle that NASA was using to lift this, heavy objects. Perhaps the example that I could identify, and it's directly related to lunar explorations in search of water, is a SCARAB. This was designed as a prospector that would use a sort of a deep coring drill and apply soil analysis instruments. Its chassis, as you can see in this figure, could transform to stabilize its drill in contact with the ground, and it could also adjust posture to ascend, steep slopes, the environments that are abundant on lunar surface. And this was tested on various locations on Earth that were similar to the lunar surface, and a fairly successful project. But in almost all of these examples, wheels can cause another major problem, which is kind of less intuitive, as we don't experience that on Earth. So let's take a look at this old video. Here, as you can see, when the astronaut drives this LRV on lunar surface, dust and regolith are propelled to atmosphere, which astronauts complained a lot about this phenomena. This is a sort of a counterintuitive phenomena. We don't experience that on Earth because we have higher gravity on Earth comparing to the moon. But as you can see in this video, all these abrasive materials, due to the wheeled mobility that is being used in this rover, are propelled into space. And this mainly happens due to the traction force generated at the contact surface between the wheel and the ground. So what we did in NASA Big Idea proposal, we proposed a solution that can offer a minimized interaction with the environment in terms of intermittent or point contact with the lunar surface, and that's in fact what I want to talk next. This is part of my PhD research. I looked into robots that can intermittently interact with their environment. For instance, here, this platform, which is called Atrius, has point contact. And I have to mention that here, the support or the boom that you are observing here, it simply has the role of supporting the robot from not falling sideways, but doesn't do anything in the plane of locomotion. And when you compare point feet walking with like flat feet walking, I mean, this is flat feet walking is how we walk. There's a fundamental difference, and that's the reduced contact surface. Of course, this may raise this question that this is flat ground walking, what you're seeing in this video, and the robot is supported, which is not comparable to what we can experience on the lunar surface. I want to invite you to search this on YouTube, point foot walking in 3D on extremely rough terrain. It's not anymore a state-of-the-art problem. It's a solved problem. And in fact, using high bandwidth controllers, you can have systems as robust as this platform that can blindly, with point contact, traverse extremely bumpy and rough terrain. What you see here is basically a blind robot with point contact and intermittent interaction with its bumpy environment, and it is still able to negotiate the environment in a stable manner. This is like they keep saying that this is like you take a pogo stick, close your eyes, and try to jump over these obstacles. It's only possible if you have a closed loop and high bandwidth controllers running in the background. So that was the first or second challenge, actually, that we could identify. What are other challenges in terms of what are other challenges that we can identify? Or what are other problems that we can identify with existing rover solutions that NASA is considering for space explorations? We can identify payload and total weight. You may ask yourself, these are ground robots, why would we care about payload? NASA's goal is to leverage investigations and demonstrations launched on commercial moon flights in near future under the Artemis program. You can imagine lightweight rovers will play an important role in our future missions and explorations. These are some of the cost or estimated cost by Astrobotics, which is one of these CLPS companies. For you to be able to put a kilogram of mass in lunar orbit, that costs $300,000, and putting a kilogram of mass on lunar surface would cost $1.2 million. So that's really important. Next or future NASA rovers, other than being efficient, to be lightweight, to be able to be launched to the lunar surface in an inexpensive way. How did we look at this problem? How did we try to overcome this challenge? In design of Husky, we decided to embed all parts, including electronic components, components of actuators, within thermoplastic materials reinforced with carbon fiber during the 3D printing process that we used to fabricate Husky's main frame. Of course, some of you might ask, embedding parts within 3D printed parts have been, it's not novel. It has been around for a while. Yes, that's correct. But embedding about 200 components within these thermoplastic materials in a fully functional platform, we consider that as a big achievement that allowed us to create a super lightweight machine at about 2 feet tall with 12 actuators. This is a decently large platform and weighs about 10 to 15 pounds, depending on sort of onboard sensors and actuators that you consider for more sophisticated tasks. So the major challenge here is to reduce payload, and we partially address that by embedding parts within components. But we also address this problem in a different way. We did try to create a design space for our system. By the way, this design space consists of all possible solutions that you can think of for a platform like this. This can be a huge space, and you see here a few examples from this space. Then within this space, we used search algorithms and computer-aided design algorithms to search for solutions that could give an enhanced energetic efficiency of locomotion, as well as a minimum payload. What you see here is just simply the total cost of transport of all of these solutions within this design space as represented in terms of intensity and color of these data points in this 3D plot. And the important finding we had, based on which we designed our solution as a front-heavy robot, was that front-heavy solutions would offer better morphology, could be considered as a better morphology in terms of offering higher margins on allowable added mass in the design while keeping the efficiency high. We also are looking into completely different forms of mobility for space explorations. And this is, let me play this video. This is motivated by some recent and emerging solutions by NASA scientists, maybe folks at JPL. So you probably have heard about Mars's Perseverance rover. And this rover has got a hitchhiker on board. This is called Ingenuity. And this little robot is essentially a rotary wing coaxial system. It's about 2 feet, and it is supposed to exploit the thin atmosphere of Mars to lift off and explore Mars surface in a very fundamentally different way than how NASA has been looking into outer space explorations than before. The way we want to look at this problem, and in fact, this is an ongoing project, and is based on looking at bio-inspired solutions. I mean, these solutions have been around for a while, but unfortunately, they have been completely overlooked for outer space explorations. They have never been considered for outer space explorations, and that's actually what is going to bring me to another project. I think I have difficulty playing this, so let's hope that this video can. Okay, this is Aerobat project, and in this project, we are trying to replicate the aerial mobility of biological bats. I mean, bats are known for the energetic efficiency of aerial mobility, and they use a very, very simple flight characteristic or mechanism to enhance their aerial mobility. They can expand their arm wings during downstroke, they can collapse it during upstroke, but replicating this simple mechanism can pose severe challenges to roboticists and those who are interested in bio-inspired designs. So we have been combating this challenge by creating bio-inspired mechanism, creating monolithic designs that put together soft and rigid components, exactly in the same way that the bat's musculoskeletal architecture works, and trying to replicate this extremely articulated body of birds and bats in general, vertebrate flyers, to achieve or to enhance energetic efficiency of aerial mobility. The quick update I can give on the status of this project, perhaps I can play this video, and that's kind of some of our recent results to bring that concept and produce the physical platform of this robot. Currently, we have this attached to a a test facility, and we are trying to better understand the complex fluid structure interactions that a platform like this can produce, and how to exploit this FSIs to kind of achieve or maximize agility and performance, and use that towards exploring unstructured environments, such as those you can find on the Mars surface. The other project that I want to mention towards the end of my talk is this platform called Harpy, and it is an ongoing project in my team at Silicon Synapse. And this is essentially a biped with 2 thrusters attached to its torso. And given that locomotion is my background, the overall idea here is to use thrusters to create machines that are super capable, machines that can jump over obstacles, machines that can push the limits of legged mobility. From a technical standpoint, something that has attracted my attention through the past several years has been, is it possible to come up with mathematical frameworks based on which thrusters and joint actions can work in unison to kind of regulate ground contact forces in this systems. And a little bit about the history of this project, and that would conclude my talk, would be the project that I initially started at Caltech back in 2018, before joining Northeastern as an assistant professor, and essentially designed and created the Harpy platform. This is Harpy at its, or Leonardo as folks at Caltech call it, at its very, very early stages of development. And here the robot is kind of using or leveraging thrusters and leg actions to kind of dynamically stabilize itself. Unfortunately, I had to leave this platform for folks at Caltech, and we are developing one version of this platform for ourselves and our students at No System, and hopefully we use that towards space explorations. with all this, I want to again say thank you to everyone for the time, and I would be more than happy to take your questions.
Thank you so much. That was wonderful. Yes, and if anyone has questions, please feel free to put them into the chat box and I can read them aloud. Takes a few minutes.
Yep.
Okay. Do the robots need an atmosphere? Oh, do air robots need an atmosphere in which to function?
Yes. And in Mars, we got atmosphere, but it's just much thinner than the Earth's atmosphere. And that kind of makes lift force generation more challenging, and that requires more efficient and more, we need to look into bio-inspired solutions.
Great. And so will anyone be using the echolocation abilities of the bat to program the bat version of a moon bat?
Well, this is something that many times, even our students or visitors ask. And yes, I know a few research teams, they are looking into that. And but we are not doing that because my expertise is not perception. I'm mostly focused on locomotion side of the problem.
Great. And then can any of this be applied to people with amputations? Is there any work into that?
Absolutely. Like the major contribution of legged locomotion community is prosthetic leg design, and this is a very hot topic research-wise. And dynamic walking is the important characteristics of humans' gaits. And what I just presented in terms of point feet walkers, it could be nicely relatable to to human locomotion and designing prosthetic devices for amputees.
Great. And then I think our final question, what kind of data would the Mars rovers and flyers be gathering?
So there are mostly, to the best of my knowledge, focused on, as you know, the ongoing research in terms of finding water on Mars, as well as on the moon. So identifying like ground composition, identifying various elements within Martian soil, identifying the decomposition of the atmosphere. These are the various, I would say, high priority and important missions that JPL is or NASA is, pursuing.
Great. Oh, I saw one more question. So do you add computer sensing for prosthetic hands so that, the hand could grab a glass but not clasp too tightly to break the glass?
Yes. This is something that we talk about it very, very often in my community. Speaking of prosthetic arms or prosthetic legs, we look at them as like completely independent units that are working closely with the operator, and for them to be able to dexterously manipulate objects in the task space of the operator, they have to have like capabilities of sensing or modulating and regulating force at the end effectors. These are like very important requirements. Otherwise, it won't be possible to use these devices, for example, to grab fragile items. So they have force feedback, they have internal controllers that work completely independent from the operator, and the operator has at the very, very high level, they just perhaps just give high level commands like grabbing a particular object through like vision-based feedback, things like that. But low-level regulations and modulations take place internally, and they absolutely have the capability to do so.
Great. Well, I think those are all the questions that we had, and that was absolutely wonderful. So thank you again for presenting and sharing all your research with us.
Thank you. Thanks to everyone. Thanks to our alumni. Thanks to our alumni center. And it was a pleasure to present this ongoing research by our students at Northeastern.
Great. Thank you again. And thank you everyone for tuning in. And I hope to see everyone next week for our next presentation.